Okay, so we've been talking about chapter two, and in chapter two, as we talked about at the beginning, really going to be kind of focusing on really electrons and sort of what happens as they sort of transition from different energy levels. We'll also, as we talked about, get into electron configuration and the periodic table and things of that nature. Um, but for the most part, we started talking about here sort of electrons, and as they transition from energy levels, they do give off sort of that energy in the form of a wave. And so we started talking about waves as well. And remember that basically a wave will sort of transmit energy through space. And we saw sort of a relationship in terms of the wave and energy. We could have sort of a wave that looks like this, a little bit better than yesterday's waves. So when we look at something like the wavelength, for example, it's that distance between peak to peak or even trough to trough to be on the bottom. Here, this is the wavelength here between those guys. And what we saw was that if we have sort of a longer wavelength, like what we have here, we usually have a lower frequency and usually results in lower energy. You kind of think about it, it's just kind of moving slower as it's kind of longer in terms of the wavelength. Over here, we obviously have a much shorter wavelength, much higher frequency, and usually results in sort of higher energy. And we can sort of figure out sort of things like wavelength and frequency by using a formula that we saw there towards the end, which was C is equal to the wavelength times the frequency, C being the speed of light, which is 3 times 10 to the 8 meters per second. Obviously, the wavelength is lambda there, which is in meters. And the frequency here is typically in reciprocal seconds. Remember that a couple common units of frequency, reciprocal seconds and a hertz, are the same thing. Basically, it's a one-to-one relationship between those two things. So if somebody says a hertz, it's really a reciprocal second, and it's again sort of equal to each other. The reason that is because that's how we get to sort of these units here for our speed of light with is meters per second. Just simply rearranging that, we could get the wavelength is equal to the speed of light divided by the frequency. Or if we have the frequency, it's basically kind of the same calculation, speed of light divided by the wavelength there will get you that. So this will allow us to figure out the wavelength and also the frequency sort of associated with it. And ultimately, overall, what we're talking about, and we'll continue to talk about here today as well, is again that sort of basic idea of we have electrons that will sort of gain energy, end up at sort of a higher energy level. And as they sort of relax back down, if you will, they are going to sort of emit that photon of light at a specific wavelength. And depending on where that wavelength falls, it may fall somewhere like we talked about sort of yesterday as well, somewhere in this electromagnetic spectrum here. And this electromagnetic spectrum has some different spots that we talked about: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. And again, if that particular wavelength, for example, falls off into the visible part of the spectrum, that is the part of the spectrum where we obviously can't see color like we see down there, Roy G. Bibb there. And, depending on where that wavelength sort of corresponds to as to sort of the color that we would see. Not all electron transitions will actually fall, in the visible part of the spectrum. You could have some maybe fall in the infrared part, maybe ultraviolet part, somewhere else, and so forth. But again, sort of those ones that do fall in that visual part of the spectrum, we're able to see color, like, for example, in the flame test that we sort of did in the experiment yesterday. Again, as you sort of heated up that sample in the flame, the electrons there were excited from the added energy. And again, as they came back down, depending on really the transition that's occurring, an electron may be going, say, from the fourth energy level to the third or whatever it may be, as to sort of what colors you see. The colors in terms of the visible part of spectrum, as we also talked about, also, follow the same sort of path in terms of wavelength and energy. What we see is red there on the right hand side of the screen is a much larger wavelength than kind of the left hand side of the screen, which is violet. And in terms of the energy of sort of those colors that we see, again, red would be lower in energy as it has a longer wavelength, and more towards the purplish side there at the end would be higher in energy as it has a smaller wavelength. Any questions on any of that stuff that we sort of talked about last time? Okay. All right, then let us continue on here. So again, we've been really talking about the idea of sort of these electrons as they sort of transfer from one energy level to the next. And the idea here is that you oftentimes hear about when we sort of talk about this sort of topic is that these electrons really do sort of gain or lose energy in only basically whole multiples of what is referred to sometimes as h times the frequency there. Let me see here. Where did that thing go? There we go. Which is h times our frequency. And this is sometimes what is referred to as sort of a quanta of energy or a packet of energy. And what does that really mean? It really means, first off, what is h times the frequency? Well, the frequency obviously is our reciprocal seconds there, our frequency. H is actually a constant. H is, as we will see, is what is referred to as Planck's constant. And Planck's constant has a value of 6.63 times 10 to the minus 34 joules times seconds. And what that means is energy is pretty much equal to h times the frequency. And if we look at sort of the units associated with here, h is joules times seconds, frequency is reciprocal seconds. The seconds will cancel each other out and we will be left with joules. So the way that we can sort of calculate the energy associated with sort of a wave, if you will, is by using that formula there. But what we're talking about is, for example, if we have, let's just draw energy levels here with these little lines. Let's just say we had an electron down here at this energy level. What that means is if this electron was going to sort of move energy levels, it would gain enough energy, and that would be an endothermic process, right? Like you put in the Bunsen burner, it gains that much energy. This electron will gain enough energy to either maybe stop here. It will gain enough energy maybe to get all the way up to, say, that energy level. And what it means when we talk about sort of quantized amounts of energy is, it will never like gain enough energy and go, well, I'll go past here and I'll just try to stop like right here, like in the middle or something like that. So it won't really do that. It'll gain enough energy either to get to this energy level, gain enough energy, get all the way up to this energy level, but you'll never sort of find one that just is like, well, I just don't have enough energy to make it up there or whatever it may be. So I sort of equate it to like when you walk on steps, sort of, when you walk up steps or down steps, right? Usually when we're walking up or down steps, we have enough energy to get to here, right? We have enough energy to get to this step. We never usually in between steps go, I'm just really tired. I don't have enough energy to get, all the way up that step and so forth. And the same idea here, if that electron was sort of making its way, sort of back down, it would lose enough energy to completely get back down to, say, this energy level. It wouldn't find itself, halfway between. Again, same idea. If you were coming down the steps, you usually have enough energy basically to go down one step, right? Go down two steps and so forth. And it's sort of the same idea when we talk about sort of quantized energy here and packets of energy and how these guys sort of gain and lose energy, as they lose energy in that form, that they're able really to sort of make these transitions from different energy levels. And, just like sort of the stair example, as we'll talk about, some people have enough energy to do basically one step at a time. Some people can, do two steps at a time and so forth. And, so these electrons sort of gain enough energy sometimes just to maybe go to the next energy level. Some gain enough energy to go to multiple energy levels above them and so forth. Any questions on that there? So this energy equation, which is an important one, this sort of quantized energy, we can basically incorporate it into an earlier equation that we saw as well, which is our C is equal to our wavelength times our frequency. So since our energy is equal to H times the frequency, if we solved our original guy like we did a second ago for frequency, frequency would be the speed of light divided by the wavelength, which then can be substituted into this equation. And that gives us that E is equal to HC over the wavelength. The nice thing about sort of this equation is this will allow us obviously to figure out the energy associated with a wave or a photon of light, because pretty much all you need to know is the wavelength there. H is a constant, which is that Planck's constant that we just talked about, that's 6.63 times 10 to the minus 34. And the C is our speed of light. So basically the top guys are both constants, our speed of light, and obviously our Planck's constant here. So by using sort of all these guys here together, it allows us to figure out the energy associated with sort of the photon of light or the wavelength. Basically, if we just have the frequency, we could figure out the energy. If we have just the wavelength, we could also figure out the energy associated with it. So those two things. You do want to be careful, again, in terms of units. As I mentioned a second ago, our H is joules times second. Our speed of light is meters per second. Again, for everything really to cancel out correctly, the wavelength here does need to be in meters. That way the meters would cancel, the seconds would cancel, and you would be left with joules. So you want to make sure that that wavelength that you're given, and again, we saw it a little bit yesterday as well. Sometimes wavelengths are given in other units like centimeters. A lot of times, sometimes nanometers is a very common one. So you do have to sometimes do a conversion to make sure you get everybody into meters. So again, all the units properly cancel out. So those equations there are important ones. You do need to obviously know those equations and know how to obviously use them by basically putting them in and plug and chugging them. Any questions on that there? Now, when we talk about sort of light and energy, there's oftentimes you'll hear this idea of what is described as sort of the dual nature of light. And what that basically means is it was found through a lot of sort of experiments that, waves have sort of particle-like properties, and particles also basically have wave-like properties. So a particle like an electron basically will have very similar sort of properties like a traditional sort of wave. This is Einstein's equation, E equals mc squared, m being mass, c being the speed of light here. And this was used with Einstein. Einstein did basically the photoelectric effect. And basically what he did is able to shine sort of light of different sort of wavelengths and intensities at pieces of metal, and was able to basically see electrons being able to be sort of emitted off the surface of metals. And it basically led to sort of this idea and sort of this confirmation of, particles like electrons, for example, have some wave-like characteristics, and vice versa. Waves have particle-like characteristics, kind of think of a wave almost as a stream of particles that are happening. So this sort of dual nature, you hear a lot about when we talk about sort of waves and again, electrons, and why electrons, the basis for a lot of what we kind of do with electrons in terms of things like electron configuration, orbitals, and those type of things, they're kind of rooted in sort of wave-like theory, even though electrons are particles, again, because they do share similar sort of characteristics. Now, when electrons sort of transition from one energy level to the next, we sometimes can see different types of spectrums. And for example, when we have something that is a continuous spectrum, that's basically when white light is passed through a prism, right, will separate out everything into specific sort of wavelengths. We basically see all the wavelengths of visible light. So you see all the wavelengths of basically visible light present, and sort of a continuous spectrum is, you know, just basically you see sort of everything coming off at once. So kind of things illuminated by sun, the sun basically, if you were sort of to look at it through something like a spectroscope and a prism, you would see sort of a rainbow sort of effect that would happen. And that's different than sort of what happens when we look at sort of the spectrum and the emission spectrum of elements. When we see the emission spectrum of elements, we see basically what is sometimes referred to as a line spectrum. And a line spectrum, pretty much like it sounds like, is at specific wavelengths. What we see is certain colors of lines. Obviously, these are all red, but there's multiple colors, obviously, in the visible part of the spectrum, that Roy G. Biv, you see all the different colors. But as opposed to sort of this kind of continuous, everybody coming off at once, we see these distinct lines sort of happening. And these distinct lines that are happening are basically occurring as these electrons basically transition from one energy level to the next. Again, as we just talked about, they do this in a sort of quantized way where they either gain or really lose lose energy in these whole number multiples. So that allows them, again, in sort of that staircase example, you know, if we have an electron, you know, it may lose energy to come down to here, and that may correspond to a specific line. Maybe this guy loses enough energy to also come down to the first one. That corresponds to maybe a different line that we see. Depending on sort of where we see these lines and sort of the energy of those lines, we can make a pretty good assumption as to, you know, is it a big energy gap? Is it a small energy sort of gap? One way we could do that is like the experiment is going to be today. Could use electron discharge tubes, basically sends an electrical current through a sample of an element, and basically obviously that current is going to excite the electrons to those higher states. And as they come back down, again, what we're looking at as they come back down is that emission spectrum. Basically, they're emitting the energy as those electrons relax back down. And that's why it's called an emission spectrum, as opposed to an absorption spectrum, where we would see what happens when they absorb the energy and they go up in terms of energy levels. Now, only certain energies are allowed for the electrons. For example, in the hydrogen atom, energy of the electron in the hydrogen atom is quantized. So again, that's just basically saying what we've been talking about, that, you know, in something like hydrogen, we would either find an electron there, we would find an electron here, we would find an electron here. And again, if they were transitioning, they would gain enough energy to make it all the way to either this energy level, or whatever energy level it may be. They would never find themselves just sort of between energy levels or something like that. And again, that idea is, as he goes this way, that basically the energy associated to do that is h times the frequency. And again, that sort of packet of energy that allows it to go all the way up. And obviously, as we were talking about, kind of coming back down, would also allow it to lose, basically, in terms of a photon. that much energy as it comes back down the other way. The only difference really in terms of the energy going this way, this is an absorption, and it would be endothermic for the atom, which means the energy would be positive going in that direction. And sort of coming back down, this would be more of an emission spectrum, and that would be more exothermic for the atom. Again, the atom would be giving off that energy, and you would end up with more of a negative value for energy. So we're going to talk about doing some energy calculations here. And it is important when we do energy calculations to actually keep the sign that we have. So if we end up with a positive number, or we end up with sort of a negative number in terms of energy, that's really important in allowing the person that's looking at it or looking at that value to understand what is happening in terms of energy. Is it being given off by the atom? Is it being absorbed by the atom? Again, negative would indicate that it's losing sort of that energy. It's being released, and positive would be endothermic. It's being absorbed. So the significance again of sort of when we look at the hydrogen atom, and we're going to see a better picture in what I drew with the actual colors, we do see these sort of distinct lines that are occurring. And it's that line spectrum, which would indicate that we have these quantized amount of energy, as we've been talking about, that they're able to basically go from one energy level to the next, rather than sort of a continuous spectrum. So, we talked about sort of the idea of a staircase for sort of quantized energy, like we've been talking about with our electrons and our thing like hydrogen and our elements, that they're either here, they're either here, they're either here. You kind of think of sort of a continuous spectrum like a ramp, if you will. That's a very badly drawn ramp, but we'll pretend it's a ramp going up somewhere. I guess I could draw the ramp more like this, I suppose. All right. That's still a very terribly drawn ramp, but we'll pretend it's not so bad. But if we were walking up a ramp, right, you basically could step anywhere along the way on a ramp, right, as you go up sort of the ramp, and you basically could be anywhere. And that's different than, again, in this sort of quantized area where you're either going to be stepping here, you're going to be stepping here, you're going to be stepping here, which means the electron will either be here, here, or here. In a sort of a continuous spectrum, sort of like the walking up a ramp to somewhere, again, technically your electron can be pretty much anywhere, which means we get wavelengths coming off everywhere for all wavelengths basically happening. And again, that's sort of the difference between sort of a quantized version of energy, which is what we see really with elements when they sort of gain energy and stuff like that, versus, something like metals that are heated, or like the sun, how it gives off energy. We see more of a continuous type of spectrum. Any questions on that there? Okay, so we're going to now talk about sort of the Bohr model of the atom, and we're going to talk a little bit about some of these things, and we'll see sort of a transition from sort of Bohr's model here into sort of a more modern version of sort of the idea of what's happening with our electrons. As we'll talk about, the Bohr model of the atom, or sort of theory of the atom, is one that works really well when we're describing hydrogen, which is why you oftentimes see hydrogen as sort of the example element used in Bohr's model. But as you sort of move away from sort of more than one electron, which hydrogen only has one electron, Bohr's model doesn't hold up very well in terms of its idea of what's happening, but it does explain, as we will sort of talk about very well, sort of the lines that we see when we look at the line spectrum for something like hydrogen. So when we look for something like the hydrogen line spectrum, sort of Bohr's model does sort of explain it fairly well, but again, it doesn't necessarily hold true as we sort of move away from hydrogen and things with much more electrons that are present. So Bohr's model was sort of that electrons in the hydrogen atom move around the nucleus in sort of this circular orbits. And this is sometimes referred to sometimes as like the planetary model. Again, we have sort of our nucleus in the middle, and around the nucleus, we have these orbits. And we have these orbits where basically electrons would be traveling in these nice circular patterns around basically the nucleus. And as we'll talk about, not so correct. They actually don't travel that way, but this is sort of how it was envisioned. And there's these different energy levels. Like, for example, this first one may be n equals 1, n equals 2, n equals 3, and so forth, as you kind of go through these different energy levels. What is n? N is basically what is referred to as the principal quantum number. And it's basically a fancy word for basically kind of the energy level. So these are the energy levels. And when we have n equals 1, that is sometimes referred to as the ground state. And the ground state is basically the lowest in energy. And it's the closest to the nucleus. Now, when we go above that, like n equals 2 through 7, for example, those are what are referred to as excited states. And those are higher in energy. And those are obviously kind of further away from basically the nucleus. And his idea was, again, we have this sort of quantized amount of energy. So what happens if we do have this electron, for example, it will maybe gain enough energy to get all the way out to, say, the n equals 3 sort of orbital, where it would be traveling in this. Again, the amount of energy required to do that would be h times the frequency. And if it decided to sort of come back down, say, to the second energy level here, that also would be h times v, this quantized energy, and it would find itself in that second orbital. This sort of transition going from the third energy level to, say, the second energy level may correspond, say, to this line that we see here in the spectrum. Maybe this electron goes from the third energy level all the way back down to the first energy level. Maybe it corresponds to this particular line that we see basically develop here. Just like sort of what we've been talking about, his model was basically this electron would either be found, say, in the first energy level, second, third, fourth, or whatever. But again, it would gain and lose sufficient amount of energy to make those transitions. And again, would not find itself hanging out sort of in the middle, along the way. And when you kind of take this into account, when we do look at sort of the line spectrum here for hydrogen, again, the differences in sort of those transitions of where those electrons are coming back down results in those different colors that we see. And we could think about sort of, for example, what we talked about when we think about the visible part of the spectrum, we think about colors, right? Our Roy, G, Biv. Remember that the red is the longer energy, longer wavelength, not energy, longer wavelength and lower energy, as opposed to the violet side, which is the shorter wavelength and the higher in energy. So if we think about our transitions and sort of these guys, here's like our red line that we would see in the hydrogen guy as a transition of n equals 3 to n equals 2 transition, right? So it's basically one energy level transition. One energy level is not going to be a lot of energy to do that transition. As you can see, they're relatively close to one another. And basically what that means is we would expect something to be lower in energy. We would expect the color to come off in terms of its wavelength to be a little bit longer. And again, that's why we kind of see the red coming off on that transition. Now, if we looked at sort of the blue transition here, blue transition started like on the n equals 5 level in terms of energy, kind of the fifth excited state. It's coming down to, say, n equals 2 if it stopped there, for example. That is a much bigger transition. We're now going from like 5 to 4, 4 to 3, 3 to 2. We're doing kind of 3 energy levels. You can see the transition just in terms of energy to do that is a lot more energy to kind of drop down. That's going to be much higher in energy. And again, that's why we kind of see, I guess, more this way here, the more bluish type color basically coming off when that electron does that transition. You can see the green is sort of in the middle. Green going from 4 to 2 is just a couple of energy levels, again, kind of in the middle in terms of that transition. So, you know, we can make a prediction based on the sort of the colors that we see as to how much energy is coming off as those electrons are transitioning down. Any questions on that there? And again, this would be an emission spectrum in terms of the atom. This would definitely be exothermic. Again, all these electrons are basically releasing that energy from the atom. And we would see for the atom overall, the energy would end up being more of a negative value as those electrons are dropping in terms of energy. And again, that's why we oftentimes will look at emission spectrums here. Absorption spectrums are pretty much the same. The only difference is the energy value would be positive and endothermic as they're gaining energy. And again, emission spectrum, they're dropping in energy. Absorption sort of spectrum, they're going upwards in terms of energy. They're gaining their energy. So here's sort of a nicer sort of picture of our what we've been looking at. And again, these sort of different transitions in sort of the Bohr model here going to give us those different colors that we see, especially in hydrogen. And again, we can see that each of these basically packets of energy, a certain amount of energy for that got to go all the way down, a certain amount of energy here and here all the way through, RH times V. And as I talked about again, when we talk about the atom itself, it's going to be losing energy in this case. You know, why do we see perhaps maybe you might see some colors that are sort of stronger in terms of the color or brighter in terms of the color? And the reason for that really is a couple of things. You know, we sometimes think about these things sort of in a one dimensional sort of thing, like we think about, oh, there's like just one electron sort of doing this transition, right? Hydrogen has one electron, so there's only one electron doing these things. But you got to remember, if you had sort of a sample of hydrogen, for example, you would have a lot of hydrogen atoms in there, right? And each one of those hydrogen atoms would be going through this process, which means you have a bunch of electrons actually doing these transitions together. So we sometimes think about these things in sort of like, oh, there's just one. But, you know, if you took something like hydrogen or you took something like neon or something like that, you know, you wouldn't just have one atom of it. You would have a lot of individual atoms, which obviously all those individual atoms have these electrons. And if you did it, you know, just like the flame test, right, when you stuck it into the flame, you know, it wasn't just one sodium atom that's sitting on that crystals and stuff like that. There's a bunch of sodium atoms, a lot of them, and they're all transitioning and doing these things sort of at the same time, which is why sometimes we'll see sort of the intensity of the flame be, or the color be sort of deeper, if you will, in terms of the color, or brighter in terms of the color, depending on how many or how much of those atoms that you have sort of doing those transitions. Now, for a single atom, when we want to sort of figure out what is going on in terms of its transition and how much energy is associated with it, we could actually use an equation such as what we see here to actually figure out the energy associated with an electron, for example, in the hydrogen atom, doing those transitions from different energy levels. And there's a couple of things here. I personally kind of round this number to 2.18 times 10 to the minus 18 joules. This is what is sometimes referred to as the Rydberg constant. It's obviously a constant value here. And that's basically the change in the energy as those electrons transition is 1 over n squared final, n being the final energy level that the electron ends up at. and 1 over n squared initial is the initial energy level that the electron was at that point. So you could use this to actually calculate the energy associated with the or the energy change within the atom as those electrons are doing those transitions. Again, as we've been talking about, we would expect sort of a negative value when we're talking about electrons transitioning downward from higher energy levels to lower energy levels. Again, they have to give off that energy in the form of a wave. And again, that would get us a negative sort of value or exothermic type value for our atom when we calculate the E. Vice versa, again, if we're sort of have an electron to start at a lower energy level to a higher energy level, we would expect in order for that to happen, basically the atom needs to gain that energy. Again, kind of like what you did when you kind of put the guy into the flame, you actually added a bunch of energy to those atoms. And that would be a more endothermic process, and we expect the delta E to be positive. Now, this E is energy, and it is the same energy that we saw earlier, which is H times the frequency, which is Hc times the wavelength. So we can incorporate that into here and basically use these guys to calculate some other things. Like, again, if we calculate the energy of this transition, we then can use this relationship here to figure out the wavelength of light that's coming off for that transition. We could also then obviously use this relationship here to figure out the frequency. Alternative to that, we could also incorporate just the straight equation that we saw previously at the beginning. And if we figured out the wavelength, we obviously could use the speed of light to figure out the frequency, again, using the same sort of guy. So you could kind of incorporate all those other equations that we saw previously into here. So you not only can calculate, if you know sort of where the electron started and where it ended, the energy change that's happening for the atom. Is it exothermic? Is it endothermic? But you also can then calculate the wavelength associated with that transition of energy, the wavelength of that photon that's associated with that transition, and also its frequency. Any questions on that? Now, a very important note when we use this equation, and it's oftentimes sort of, asked together, if you will, in terms of questions of, you're given sort of a transition for these electrons going from one energy level to the next, and you're oftentimes asked, hey, calculate the energy, calculate the wavelength, calculate the frequency. So if you're given some of that information about an electron transitioning, you definitely should use this equation here, right, for the energy. The problem is this equation, when you use it, can give you a positive or negative number, which when you do the calculation for energy, you should keep it as either positive or negative, depending on sort of what you get for the answer. With that being said, if you're going to continue on and use that energy value to kind of calculate something like the wavelength or something like the frequency here, you then need to, especially if it is negative, you need to turn it into a positive number for the calculation of the wavelength or the frequency. So when you calculate the wavelength or the frequency, you should always end up with a positive number. And sometimes people, they keep the negative for the energy, which you should keep the negative for the energy calculation. But when you go then use it in the calculation to calculate a wavelength or frequency, we basically just turn it into a positive number. So you don't get a negative wavelength or frequency. So you can't have a negative wavelength or frequency. Number doesn't change, just takes it from negative to positive. So you don't end up with a wavelength or frequency. We're going to do some examples here in just a second, and hopefully it'll make some sense there. Any questions on that? So the model, as we talked about, and as I mentioned sort of earlier, does work really well you know, for what we see happening in the hydrogen atom. It does sort of talk about it again, only being allowed the electron to be found in a certain orbit, traveling in these circular directions. And as the electron becomes more tightly bound, its energy becomes more negative relative to zero. So as the electron is brought closer to the nucleus, energy is being released. So that's just, again, basically talking about what we've been talking about, that, you know, as the electron goes from that higher energy level to a lower energy level to a lower energy level, it's coming closer to the nucleus. It's going to be giving off more energy. And again, the energy is going to be negative in that case for the atom, because it has to release it as it works itself back down closer to the nucleus from a higher energy level to a lower energy level. Now, as I mentioned before, the Bohr's model is sort of incorrect, as we'll talk about here in just a second, in terms of really how electrons move around sort of the atom. They really don't move in these circular patterns. And as we'll talk about, you really don't know at any given point in time sort of how an electron is moving. You can't just say it's going around in a circle. You can kind of put your finger there and eventually it'll come back around and sort of hit it. And we'll get into that, but it does work pretty well for hydrogen because it really has only one electron. But as you sort of incorporate multiple electrons in atoms, that sort of planetary model or orbital sort of our orbit model, it doesn't really hold up. So why don't we look at an example here? Here's a few different transitions. And for each of these transitions, why don't we want to figure out the color light that's going to be emitted by an electron in hydrogen as it falls from each of these sort of guys. Since it is the visible part of the spectrum and the color of light, it probably will be in nanometers. So figure out the wavelength in nanometers. Why don't you also figure out the frequency associated with it? And why don't you figure out the energy associated with it? So for each of these transitions, take a few moments here, several minutes. And for each of these transitions, figure out the wavelength, the frequency, and the energy associated with it. And a reminder that nano is 10 to the minus 9. And speed of light, in case you forgot, is 10 to the 8 meters per second. So for A, B, and C, you should have 3 answers, really, or maybe 4 if you got the color that's going to come off as well. For each of those things. So take some time and work them out, and then we'll go over it together. Again, making sure everybody knows how to do these calculations, as they are pretty much the calculations you're going to be doing today in lab. So take a few minutes and see what you come up with, and we'll talk about it in just a bit here. Hopefully you're back. Hopefully you make some progress on this example. So we're going to kind of go over it here again and make sure everybody's on the same page in terms of what's going on. So we have 3 different problems here, basically 3 different sort of transitions of electrons in the hydrogen atom here. They're falling down, so they're going obviously from a higher energy level to a lower energy level in each of these cases. So let's take a look at A first, and we're going to try to obviously figure out pretty much everything here, the wavelength, the frequency, and also the energy associated with that electron transitioning. So let me see, I got somewhere to write. I think here will work. So our first one was 5 to 2. So we're going from n equals 5 to n equals 2. And obviously this would be our final. I'm sorry, this would be our final. That would be our initial. And since we're talking about, again, an electron transitioning from one energy level to the next, we do want to use our energy equation that we just saw, which is the change in energy is equal to Rydberg's constant. And again, I'm going to use the rounded version of it. 1 over n squared final minus 1 over n squared initial there. So really we have everything that we need to calculate the energy change for the atom here by just really plugging it in. So that's really a good place to start. So we'll do that. And our change in energy in this case, again, would be minus 2.18 times 10 to the minus 18 joules, 1 over our final guy that's squared, so 2 squared is 4, minus 1 over our initial guy squared, so 5 squared is 25. So if we do all that good stuff here, basically take 1 divided by 4 minus 1 divided by 25, then times it by 2.18 to the minus 18, which is also negative. Looks like we end up with a negative 4.58 times 10 to the minus 19. The units here would be joules. Now, a couple of reminders, as we talked about, I think yesterday as well. Again, you definitely want to make sure that you're using your exponent button here when you're punching these guys in. If you find yourself with sort of the front part of the number okay, but the exponent part not so okay, it might be how you're punching it in with your in your calculator. So make sure, again, you use that either that E button, that EXP button that we talked about, or that kind of times 10 part that you do have to put parentheses around. Now, this is the energy calculation. And as we were talking about before, we did end up with a negative number. And that does make sense if we think about what's happening here in the transition. We are starting at like the n equals 5 energy level, which is much higher than the n equals 2 energy level. And this electron is coming down. In order for it to come down, as we've been talking about, it has to give off that energy in the form of a wave or a photon. And that would be an exothermic process, which we would expect our energy value here to be negative. So the negative value that we get here is important, and you do need to keep it for the energy calculation, as it tells people that this is an exothermic process for the atom. Any questions on that part of that there? Now, since we're going to calculate the wavelength and the frequency, we have a couple of ways we could kind of approach that at this point. But one way that we would want to sort of probably start with is using the relationship again that E is equal to H times the frequency. And remember, again, we could also use the HC over the wavelength, which means really at this point you have two options. You could either calculate the wavelength if you want, or you could calculate the frequency. So for example, I will do the frequency first by just using this part of it. So if I just use this part of it, the energy is equal to H times the frequency. That means the frequency would equal E divided by H, again, dividing this to the other side. Now, this is where we were talking about a second ago that although we definitely want to keep the negative sign here for the energy, we want to get rid of it when we go into this calculation, because we do not want a negative value for our frequency. Technically, this is basically the energy change for the atom, basically. And we could change it basically to a positive number to tell us basically how much energy is associated with just the photon of light. But the easy way to remember is basically get rid of the negative here. So we're going to use the same number, but the positive version here, so that we do not end up again with a negative frequency. H is our constant, which is our Planck's constant, times 10 to the minus 34 joules times seconds. And again here, want to definitely make sure exponent button is being used. 4.58, exponent button, negative button 19, divided by 6.63, exponent button, negative button, not the subtract button, 34, gives us a frequency in this case of 6.91 times 10 to the 14. Our units in this case are joules will cancel. is basically 1/seconds or reciprocal seconds, which is the units associated with frequency. And again, that is the same thing as a hertz. Question on that calculation there. The 6.63 times 10 to the minus 34 is H. It's a constant. That's Planck's constant. So you always have that number. That is a constant value that's kind of like the speed of light. It's a constant value as well. Other questions on that? Okay, so now that I have actually the frequency, I actually still have a couple ways that I could get to the wavelength. So one way that I could get to the wavelength if I chose was I could just go back to that original equation that we saw, which is that C is equal to the wavelength times the frequency. Because now that I have the frequency, I could solve for the wavelength, which would be C divided by the frequency. And that means that the wavelength here would be the speed of light, which is a constant, divided by the frequency that we just calculated, 6.91 times 10 to the 14 reciprocal seconds. Again, making sure we use our exponent button here, 3 to the 8, divided by 6.91 exponent 14. Looks like we end up with a lot of zeros there, but we'll go with 4.34 times 10 to the minus 7. 4.34 times 10 to the minus 7. Units here, seconds and seconds cancel. These are meters. Remember that we wanted nanometers, and that's because we're talking about the visible part of the spectrum here. So to do that, nano is our 10 to the minus 9. And remember that when we say nano is 10 to the minus 9, what that means is in 1 nanometer, there are 10 to the minus 9 meters. So again, as we talked about yesterday as well, very common, people will sort of backwards these guys up or mix these guys up. So we do want to go with 10 to the minus 9 meters on the bottom, 1 nanometer on the top. We're going to take the top and multiply, divide by the bottom. The bottom basically is 1 times 10 to the minus 9. And if you do that, you end up with 434 nanometers. And to answer the question about sort of what color we would expect, 434 puts us somewhere in that bluish range in terms of color. First off, any questions on that sort of approach there? Now, as I mentioned earlier, you know, we could have, if we wanted to, at this point, or actually after we did the first part of the calculation there, we could have used our energy value and this relationship and actually calculated the wavelength first using E is equal to HC over the wavelength, which means that the wavelength would equal EC, I'm sorry, not EC, HC. HC over E in this particular case. And again, the top two are really constant. So that means that the wavelength would be our Planck's constant times our speed of light. And we could divide it by our energy. Again, we're going to use the positive version of it so that we do not end up with a negative wavelength. And if we do all that good stuff there, again, we should end up with the exact same number that we got on the right-hand side there, which should be, just to verify, make sure, 4.34 times 10 to the minus 7. Joules will cancel, seconds will cancel, and that would again leave us with meters, which we could then do our conversion into nanometers like we did on the other side there. And that will give us 434 nanometers. So again, this shows you that if you wanted to, you could have went from energy and calculated the wavelength up front. You could have done what we did and got the frequency and then the wavelength. So there are a few different sort of pathways that you could take. You can see here, hopefully, that they all sort of give you the same sort of outcome. Any questions on any of those calculations, where any numbers came from or anything like that? Okay, then let us look at the next one, which is, in this one, we are going from, in B, n is equal to 4 to n is equal to 2. So again, we are still transitioning downward. So we can make a pretty safe prediction that we should see, much like the previous one there, we should see a negative value for the energy as it's exothermic for the atom as it is going downward. So we will start with our same spot, which is our energy. So our change in energy going to be our minus 2.18 times 10 to the minus 18, or Rydberg constant. Obviously, this is our initial, that is our final there. So 1 over our final squared, which would be 2 squared, this is 4, minus 1 over our initial squared, which is 4 squared, which would be 16. And again here, 1 divided by 4 minus 1 divided by 16 times 2.18 to the minus 18, which is negative, going to yield us a negative 4.09 times 10 to the minus 19 joules. So as we sort of correctly predicted here, we do see the negative sign, which makes sense. Again, we're transitioning from the 4th energy level down to the 2nd energy level. So we would expect that energy to be given off in the form of a wave or photon of light. And that means that the atom itself is basically giving off that energy. And that is why we see our negative number. As we've talked about just a second ago, at this point, again, we do have several couple of options as to where to go with. So again, I'm going to go with the frequency using E is equal to H times the frequency. I mean, our frequency is our energy divided by our H. Just like we've been talking about, we are going to keep this negative for our energy calculation. We're going to get rid of it for our frequency calculation, our wavelength calculation. So we're just going to make it a positive number. Number doesn't change, just the value becomes positive, so we don't get a negative frequency. Again, our Planck's constant, which is our minus 34 joule seconds, and that will yield us, looks like maybe 6.17 times 10 to the 14. Again, joules will cancel here, leaving us with seconds on the bottom. Reciprocal seconds are, again, that is the same thing as a hertz. Any question on that calculation there? And at this point, what I'm going to do is I'm just going to actually go into just this equation here. Again, you could go back to the energy one and use E is equal to hc over the wavelength. It should come out exactly the same. We're going to go with our wavelength. It's our C divided by our frequency, 3 times 10 to the 8 meters per second, divided by the frequency we just got there. And again, making sure we're using our exponent button, 3 exponent button 8 divided by 6.17 exponent button 14. And that looks like it gets us a 4.87 times 10 to the minus 7. Again, seconds cancel here, leaves us meters as our units. We did want nanometers, so we will do that conversion. Again, same conversion that we've been talking about, 10 to the minus 9 meters is 1 nanometer. Meters will cancel since we're basically dividing top by the bottom. And we're going to take that and divide it by minus 9, going to yield us 486 or 487, I guess. We'll go with 487, just sort of the rounded number. Mike got 486, it's okay. So 487 nanometers. And that would then be somewhere in the greenish area, I think, in terms of color. Any questions on that there? And again,
I have a
like,
question.
yeah.
Um, Sorry, my baby's crying, but how did you know the range for the colors, like
Yes.
487 and screen?
So it would go back to, let me actually get back to that. Where is that one there? Yeah, back here. It would go back to electromagnetic spectrum where it broke it out. Where is that? It's way back there. There it is. So somewhere in this range. So, you know,
Oh, okay.
these are basically nanometers. So that's like 500 nanometers, 600, 700 nanometers, and like 400 sort of nanometers. So like 487 is close to like 500 nanometers, which would put you kind of in the greenish area. And I forget what our first guy was there, but it was 4 something, I think, as well. 434. So 434 would put you, a little bit back this way and stuff like that. So that's how you would know. So when we look at this, this is basically 400 nanometers over here. And this guy is 700-ish nanometers in that area, that range.
Great, thank you.
You're welcome. Other questions? And again, on that last one, you could go and, like I said, use E equals HC over the wavelength as, again, another approach. And you should get pretty much the same answer. Maybe slightly different if you round it a little bit, but pretty much almost identical there in terms of what you should get. There we go. All right, so we did here. We did the first one, second one. So the last one is 3-2. So we'll finish up that last one here. Okay, so this last one is going from the third energy level to the second energy level, looks like. So let's take a look at that one. N equals 3 to N equals 2 is our transitions. And again, this is going to be our initial and our final. And just like we've been doing, we'll start with our sort of equation that basically handles those transitions using our Rydberg constant. And our 1 over our final, which again is 4 in this case, 2 squared. 1 over our initial, which is 3 squared, which is 9. And in this case, 1 divided by 4 minus 1 divided by 9 times 2.18 to the minus 18. Again, that's negative as well. So it does look like we are going to hit minus 3, we'll call it 0.3 times 10 to the minus 19 joules. Again, as we've been talking about with all the other couple of examples that we did, this is exothermic for our atom, which again does make sense as we are going from the third energy level down to the second energy level. Again, going to be giving off that energy. So the atom itself will be sort of negatively charged, not negatively charged, I'm sorry, will give off the energy and have a negative energy change, which indicates exothermic. So in this case, we can then go with, just like we've been doing, why don't we mix it up here? Why don't we go with our E equals HC over the wavelength? Why don't we do the wavelength first? So the wavelength in this case would be HC over E, in case we want to go that route first, times 10 to the minus 34 joule seconds. Again, that's a constant, and our speed of light is also a constant divided by our energy. So again, going from our wavelength, we want to get rid of our negative here so we don't end up with a negative wavelength. And in this case, joules will cancel, seconds will cancel, and this will give us our wavelength here in terms of meters. 6.63 exponent negative button 34 times 3 exponent button 8, it equals divided by 3.03 exponent button negative 19. That's going to give us a 650, we'll call it 656, I guess. 6.56 times 10 to the minus 7 meters. Doing our conversion to nanometers like we did previously. We're basically going to divide that number by 1 times 10 to the minus 9. That's going to give us 656 nanometers. That's somewhere in that probably kind of orangey red sort of area of the spectrum. And we need frequency. So if you wanted to, you could go with this guy here. Actually, can use this to calculate the frequency, C divided by the wavelength, taking our 3 times 10 to the 8 meters per second divided by our wavelength. Now, a reminder that we don't want to use the wavelength in nanometers because the units will not cancel. We actually need to use the units in meters so that the units do cancel. So again, you want to be careful of units when you're using these equations. Make sure everybody's in the proper units so everything cancels. 3 to the 8 divided by 6.56 to the minus 7, looking like it's giving us 4.57 times 10 to the 14 reciprocal seconds, which would be our frequency. Question on any of those guys there? Now, let's see here. There's actually, I think, another question in addition to calculating all that stuff, which was the actual question is, I guess, which transition results in the longest wavelength of light? So we can see that the transition that results in the longest wavelength of light, if we kind of look at it, what we just calculated here was 656. What we calculated previously, I think, was in the 487. And then obviously previously that was 434. This guy was the shortest wavelength, which means we would expect it to have the highest energy. While this guy at the end here was the longer wavelength, and it should have the lower energy. So if we just look at the energy values between those two, we have 303 basically. And if we come back to our first calculation there, where's our first calculation? We ended up with 458. So basically this is a higher energy because it has a shorter wavelength than what we saw in terms of that transition at the end. Again, this is a longer transition, right? Going from the 5th energy level all the way down to the 2nd energy level. It needs to release a lot more energy to do that, which is why we see a bigger number here. And because it releases more energy, it corresponds to a shorter wavelength, and why we're kind of more at the blue color of the visible part of the spectrum, as opposed to here, which is a much shorter transition going from the 3rd energy level to the 2nd energy level, and thus we see a lower energy required to do that, less energy needed to be given off to do that transition, corresponding to a longer wavelength. And then obviously our guy in the middle is in the middle basically of those two. This is a longer transition than the last one, but a shorter transition than the previous one. And again, we see an energy level that kind of falls between the two, and a wavelength that also, is between the two as well. Any questions on how to do those calculations there? Definitely the calculations that we're going to be doing here in lab in just a bit, and all 3 of these calculations. Any questions on how to calculate the wavelength, how to calculate the frequency, how to calculate the energy associated with a transition of an electron from one energy level to the next? And again, those are, I would say, the 2 common sort of errors as I've been talking about as we've been doing these. First off is the normal not using your exponent button properly on your calculator and punching these things in. The second one is not getting rid of the negative in the energy one as you do the other calculations. So just to reiterate, when you do the energy calculation, you should absolutely keep the negative if you get a negative. But again, you need to get rid of it for frequency and wavelength. You should never end up with a negative frequency or a negative wavelength. So wavelength should always be positive, frequency should always be positive, and energy can be either negative or positive. So again, just keep that in mind as you do these calculations. Again, very common errors that people make. Any questions on any of that stuff there?
I have a question.
Yeah.
Okay, so to summarize, when you calculate these kind of problems, I'm guessing it will be on the test. So you need to calculate frequency, wavelength, change in energy, and color wavelength. Is there anything else? Okay.
No, I mean that could be the questions. Yeah. So you need to be able to kind of, not necessarily you might have to do that all in one question or something like that, but you do need to be able to, for electrons transitioning, be able to calculate basically those, I guess, 3 things basically,
Okay.
and probably have an idea as to maybe what color it might be good as well.
Okay.
Definitely the calculation part, those 3 things you need to be able to do.
And the frequency, it's the units, it's S-1, correct? And V equals S-1?
Yeah, so the units for frequency is typically reciprocal seconds, which is that
Okay.
S to the -1, or sometimes it's written like that. And a reminder that you'll sometimes see frequency given in the units of hertz.
Oh, hertz. Okay.
Hertz is the same thing, basically. It's a one-to-one relationship. So they're kind of like the same thing. So those
That's
are 2,
-1. Okay.
yeah. So there are 2 common sort of units of frequency, which is a hertz or reciprocal seconds. So you could also, if you wanted to, if we were going to convert this into hertz, it would be the exact same number. The only difference is you just write hertz.
And then wavelength is nanometers. Change in energy is joules. Okay.
Yeah, so in terms of units, energy usually is in joules and what we deal with, sometimes kilojoules, but usually joules. And wavelength is typically, for the most part in sort of this chapter, usually is either in meters or nanometers in terms of what you need to give the answer in. But definitely though, if you're using it in, these type of formulas, the wavelength does need to be in meters to properly cancel out. So although you may be asked to solve for nanometers like we did here in these problems, when we did the actual calculations and stuff, you do need to use it like in meters and stuff like that, so everything cancels out correctly.
Do we need to memorize the color of the wavelength, the spectrum, the table, like have a general idea?
I'll be honest, I don't know if I would ask you exactly what color it is, per se, but what you need to know is, again, like we talked about yesterday, I think, which color is higher in energy, lower in energy, and stuff like that. So in terms of a question like this, I don't know if I would ask you, like on an exam or quiz, what color that corresponds to. But I definitely would ask you, to calculate those 3 things.
Thank you.
Yep. Other questions? Okay, so I think it's a good place to lay it up. That definitely covers all the calculation we're going to do for lab as well.